All right, everybody. We are now on 5.3, back to 5.3 from 5.7, right? Why to skip? Who knows? Okay, so today is just about properties of rational functions. So we will cover finding the domain of a rational function. Most importantly, we will cover what vertical asymptotes, horizontal asymptotes, and what oblique asymptotes are. Most importantly, what an asymptote is and what do they have to do or how are they related to rational functions. Okay, yeah, and then this will lead us on to 5.4 and 5.5 when we start graphing rational functions. Okay, so let's just start by finding the domain of a rational function. We know that for rational functions, in order to find the domain, all you have to do is take the denominator and set it equal to 0. Then solve for x. So for number 1, oh wow. Our domain, we take x plus 5, the denominator, and set it equal to 0. All we have to do now is solve for x. And you get x cannot equal -5. The reason it can't equal -5 is because it will make the denominator 0, and we can never have 0 in our denominator. Okay, perfect. Once again, what's this in interval notation? You can be any number you want except for -5. So we would go -infinity to -5, union -5 to infinity. All right, that one's easy, right? Next one. Same exact process. These are all rational functions on this page. So for this domain, we take the denominator and set it equal to 0. We can solve this using the square root method. You square root both sides, and we'll get x cannot equal ±2. So that is the domain for this rational function. Interval notation, -infinity to -2, union, -2 to 2, union 2 towards infinity. Okay, perfect. Not bad. Kind of just a refresher, right? Okay, number 3, same thing. Domain. Take the denominator, set it equal to 0. Square root both sides, but what happens? The square root of -1 is going to give us imaginary values. You'll get x cannot equal ±I. But how do we state that for our domain? What's this trying to tell us? Well, if you end up with your domain can't equal imaginary numbers, this means that your domain must be all real numbers. So our domain is -infinity to infinity, because what this is saying is that, hey, imaginary numbers are the only numbers that make this function undefined, so therefore you can use a set of all real numbers. Okay. Next. Okay, so green, now we're in the purple. And for domain, once again, take your denominator and set it equal to 0. You'll get x cannot equal 1. Perfect. That was so easy, right? I mean, even in interval notation, you'll get -infinity to 1, union 1 to infinity. Okay, but I don't want to leave this problem yet because I want you guys to start noticing things. You guys are at this college algebra level, and you guys should look at problems and things should start popping into your head, ideas, when you see something familiar. You should have saw this numerator from the beginning and thought, hey, isn't that factorable? And it is. It's definitely factorable. If you factor this, you get x plus 1, x minus 1 over x minus 1, where your x minus 1s will cancel and give you a new function of x plus 1. Well, now the big question is, does the domain change because we have a new function? And the answer is no, it does not change. Since this function came from this original rational function, so we just came from a linear to a rational. So no matter how many times you reduce it, this function still has to abide by that domain, no matter what. So once we get into vertical asymptotes, or just asymptotes in general, if you ever cancel out part of your function in the denominator, then this value of x equal to 1 becomes a hole in the graph. This is now a hole in the graph. Meaning, if I were to graph x plus 1, my graph would look like this. There would be a hole in the graph at 1, 2, only because we still have to obey the original domain. Just because you cancel terms out doesn't mean that you have a new domain. Whatever simplified function you get has to still abide by all of this domain. Okay, so most important thing to note is that if you ever cancel out a piece of your denominator, just know that it will create a hole in the graph. Okay. Things to think about, right? Things to notice. You guys should look at problems and be like, hey, that looks factorable. Let me try it and see what happens. So you want to start catching on to these things. It makes work a lot easier, trust me. Just like the synthetic division parts. You guys were trying to do synthetic division on a 3-term polynomial that was definitely factorable by normal means. You could save yourself a lot of time if you just notice this stuff. Okay, now a humongous page of definition. Now we get into the definition of asymptotes. Ooh, look at this fancy definition. Let R denote a function, a rational function at that, if x approaches negative infinity, or as x approaches positive infinity, the values of the function r of x approach some fixed number L, then the line y equals L is a horizontal asymptote of the graph of R. All right. So what that means is, if we look down below here, the first picture represents the definition of a horizontal asymptote. So what we're saying is that, let's see, this is the red line. The red line's a horizontal asymptote. So what we're saying is that as x approaches infinity, we see that this part of the function starts to get closer and closer to this dashed line. Well, x can approach positive infinity or x can approach negative infinity. And if that function gets closer and closer to a horizontal line but never touches, then that line is called a horizontal asymptote. It is a line that you approach but may never touch. But the touching part depends on what type of asymptote you have. So Vertical asymptotes cannot be crossed. Horizontal asymptotes and oblique asymptotes are the only asymptotes you can intersect or cross. So keep that in mind. And there's a reason for that. We'll get into that in a moment. Okay, so that's a horizontal asymptote. The next definition up there says, as x approaches some number c, the values of the rational function, the y values, will either approach infinity or negative infinity. Then that line, x equals c, is called a vertical asymptote of the graph of R. Just like we have right here, second picture. So as we get closer and closer to this number c, we see that the graph starts to head towards negative infinity, meaning we will never ever touch that x value. So as the graph approaches this x value, it's either going to head towards negative infinity or it's either going to head towards positive infinity and never ever touch that x value. This is why vertical asymptotes can never be crossed. Well, there's also one more reason, which we'll get to in a second. Okay, right now we're just ironing out the details of what an asymptote is. And for now, the simple, plain English definition that I wrote on there is an asymptote is a line that the graph of a function approaches. So your function can approach a horizontal asymptote, your function can approach a vertical asymptote, or your function can approach, what's better, there's my slant, can approach an oblique asymptote, or it can come down and get really close and take off, come this way and take off. That's what an asymptote is. It's a line that our function approaches. Okay, more definition. Vertical asymptote in the form of x equals c describes the behavior of the graph when x is close to some number c. The graph of the function will never intersect a vertical asymptote. I mean, I guess I could draw pictures so it doesn't just seem like I'm talking, right? So for a vertical asymptote, let's say that my number c was here. Here's my vertical asymptote, and what we're saying is that as we approach c, one of my tails can head towards infinity, and one of my tails can head towards negative infinity. Or the opposite can be said. One tail, the tail from the left, can go down to negative infinity, and the tail from the right can go up to infinity. Or two other things can be said. As you approach a vertical asymptote, both tails can head towards infinity, or both tails can head down to negative infinity. So that's how vertical asymptotes work. Okay. Horizontal asymptote in the form of y equals some number L describes the end behavior as the graph approaches infinity or negative infinity. The graph of a function may intersect a horizontal asymptote. So like I said, horizontal asymptotes can be intersected, verticals never. All right, horizontal asymptote, I know there's pictures below, but I'll draw more. There's my graph, and let's say I have my horizontal asymptote here. And what we're saying is that as x approaches infinity, so as x is headed that way, our graph can come down and get super close to that horizontal asymptote. It could intersect, or it may never ever intersect, but you are allowed to intersect if possible. Or if x is headed towards negative infinity, then my graph could come down and look like this. Or my graph could also come and look like this. You'll get really, really close to the line, but you may never, ever touch. May is the key word here. Okay, those are horizontal asymptotes. And then in oblique asymptote, as x approaches positive or negative infinity, the value of a rational function, r of x, approaches a linear expression, y equals, that should be mx plus b, but whatever, ax plus b, then y equals ax plus b is an oblique linear asymptote. The graph of a function may intersect an oblique asymptote. There's a nice picture down there for your oblique asymptote. Oblique is just linear, it's a line, and you see that these graphs down below, they get really close to it, but they don't touch it. So, oblique is just linear. Okay, perfect. Okay, excellent. So, those are the definitions of asymptotes. You have a vertical, horizontal, and oblique. There is one more, but we'll learn it at the end. It's the easiest asymptote. It's the easiest asymptote to know. Okay, so remember multiplicities for x-intercepts and zeros, you would touch or cross the x-axis. Well, now there are actually multiplicities to asymptotes. All right, well, to vertical asymptotes at that. So number one, if the multiplicity of the zero that gives rise to a vertical asymptote is odd, meaning if our linear factor in the denominator is odd, as an odd power, the graph will approach infinity on one side of the vertical asymptote, and the graph will approach negative infinity on the other side of the vertical asymptote. So let's see what that means. So look at our example function right there. You're given f of x equals 1 over x minus 2. Well, if you solve the denominator for x, you would get x cannot equal 2, which creates this vertical asymptote. And with that being said, how many times does x minus 2 show up? What is the power on that x minus 2? That power is 1, which is odd. And it wouldn't matter if it was 1, 3, 5, 7, any odd number. No matter what, you see that if you have an asymptote, a vertical asymptote with an odd multiplicity, one tail goes to infinity, the other tail goes to negative infinity. That's it. So if you have an odd multiplicity on a vertical asymptote, one tail goes to infinity, one tail goes to negative infinity. Same can be said over here. All we did here was put a negative in front, and if you think about transformations, what does the negative do in front of a function? It flips it over the x-axis. So essentially, we just took this tail, flipped it up there, took that tail, and flipped it down there. That's it. So, in odd multiplicity, one tail goes to infinity, one tail goes to negative infinity. Okay, so that's odd multiplicities of vertical asymptotes. Next is even multiplicities of vertical asymptotes. Even multiplicities, okay. So if the zero that gives rise to a vertical asymptote is even, the graph will approach infinity or negative infinity on both sides of the vertical asymptote. So this time, both tails can head up or both tails can head down. Okay. So what that means is, look at our example function. You're given 1 over x minus 2 squared. If you solve the denominator for x, you get x cannot equal 2, but this time it has a multiplicity of 2. It shows up twice. It's an even multiplicity, 2, 4, 6, 8, whatever. As long as it's even, you will see your tails head towards positive infinity. Both tails will head towards positive infinity. Or both tails will head towards negative infinity if, given the same function, it's negative. So now you put the negative in front, those tails just flip over the x-axis and now head towards negative infinity. Look at your denominator. You have a multiplicity of 2. It's an even multiplicity. So once again, if you have an even multiplicity on a vertical asymptote, both tails will head up or both tails will head down. And that's it. That is, well, it's not for the whole thing, but that's it. That's multiplicities of vertical asymptotes. Okay. I mean, your takeaway is odd multiplicity, you got that. Even multiplicity, you got this or this. Oh wait, even better. Odd multiplicity, you got that, and then that. Okay, I'm looking at the camera, and then, yeah, you get it. Math is a dance. Okay. All right, next one. All right. Locating vertical asymptotes. I'm not even going to read this paragraph to you because I'm going to make it really, really simple. I'm just going to read the in English part to you down below. How do you find a vertical asymptote? Easy. You set the denominator equal to 0 and you solve for x. Whatever x values you get, guess what? Those are not only part of your domain, those become your vertical asymptotes as well. It's easy money and it's free points. So if you have your domain, you have your vertical asymptotes. Felt like one of those memes. If you have your domain, okay, you get it. All right, you have your vertical asymptotes. So all we want to do is find the vertical asymptotes and plot them. Just graph them. That's it. So to start with, number one, the domain of our first function. We don't have to do interval notation. We'll keep it really simple. The domain is x cannot equal 1. And therefore, this is why I say easy money. The vertical asymptote becomes the vertical line, x equals 1. That's it. They go hand in hand. Nothing to it. So all we're going to do is plot the vertical asymptote, nothing else on the graph to the left. And here is 1. And look at our vertical asymptote. That's x equals 1. Nothing crazy. That's it. That's all we have to know. Vertical asymptotes are easy. Let's try it again. Over here. Domain is x cannot equal plus or minus 2. Which means your vertical asymptotes are x equals -2 and x equals 2. Now all we have to do is plot them. There's 2, there's -2. Done. Nothing crazy. Keep it simple. Keep it really simple. If you have your domain, you have your vertical asymptotes. That's it. Hand in hand. Next one, 3. Domain. Guess what the domain of this one is? All real numbers, which means there are no vertical asymptotes. I think these are the exact same functions from the very first page. That's why we're doing this. Well, I'm doing this so fast, right? So there's no vertical asymptotes, so no need to graph anything here. 4. I guess almost the exact same function. Okay. Let me zoom in a bit. This is going to take a little work. the domain of this function, you'll take x squared plus 4x minus 21 and set it equal to 0. Factor that, you should get x plus 7x minus 3 equal to 0. X squared 3, 7, 4, good. And you'll get x cannot equal negative 7, and x cannot equal 3. Okay. So, domain and vertical asymptotes go hand in hand. So you'll have x equals negative 7, and x equals 3. But I know you're clever, more clever than that, right? Because I told you to notice things. And you probably were like, hey, that numerator is factorable. Let's see what happens when we factor it. So we'll do that down here. If you factor that, our function g of x becomes x plus 3 over x minus 3 over x plus 7, x minus 3. Where your x minus 3's cancel, and we get our new function of g of x equals x plus 3 over x plus 7. Okay, now two big questions. First big question is, does the domain change? And that answer is no. This function still has to abide by that domain. So that's one big question answered. The second question to be answered, big question, is what happens now to that vertical asymptote of x equals 3 since we canceled it out of the denominator? And if you remember from the very first page, that what I said is if you cancel any piece of your denominator out, that piece that you cancel now becomes a hole in the graph. So x equals 3 is a hole. X equals 3 is a hole, and the only vertical asymptote we have here is x equals negative 7. So that's all you have to plot. Let me see. 4, 5, 6, 7. And here is my vertical asymptote. If I wanted to plot the hole in the graph, I would plug 3 into this function. And let's see, hey, why not? It's good practice. Find where the hole is. The hole exists, and you'd have g of 3 equal to 3 plus 3 over 3 plus 7, and you'd get 6/10, or divide by 2, 3/5. So when x is 3, you're gonna have a hole in the graph at 0.6. So somewhere around there. So once again, if you cancel a piece of your denominator out, that vertical asymptote now becomes a hole in the graph. Okay, fun stuff. Vertical asymptotes are easy. Keep it really simple. If you have your domain, you have your vertical asymptotes. But then if you cancel a part of the denominator, that vertical asymptote now becomes a hole in the graph. Okay, simple enough. Now we get to the hard stuff. Horizontal asymptotes. Look at all that nonsense down there. Okay. Let's see. Emails. Okay. So first definition is, what is a proper rational function? If a rational function, r of x, is proper, then the degree of the numerator is less than or smaller than the degree of the denominator. So that's what it means to be a proper rational function. Being a proper rational function is the same thing as being a proper fraction. The numerator always has to be smaller than the denominator. But this time it's in terms of exponents, degrees, or powers. Okay, so that's what it means to be proper. Now, finding a horizontal asymptote. Look at all those rules. 1, 2, 3, 4. Okay, so if f of x, or let f of x, equal some rational function in proper form, once again, what you're seeing in that confusing print in the numerator and denominator is just a polynomial in standard form. You go from highest power to lowest power in the numerator, and in the denominator, same thing, highest power to lowest power in the denominator. That's what that fancy looking notation is. Okay, moving on. All we actually want to look at is the leading terms and the powers to go with these 4 rules. Okay, rule number 1 of horizontal asymptotes. If the degree of the numerator n is less than the degree of the denominator m, then the x-axis, which is the horizontal line of y equals 0, is your horizontal asymptote for the graph. Easy money. So if the numerator's degree is smaller than the denominator's degree, then we will have an automatic horizontal asymptote of y equals 0. So let's work some examples as we go through these. Look at number 1. Let's try to apply the first rule we learned. If it doesn't work here, then we'll look at the other rules. So rule number 1 said the degree of the numerator. What is the degree of this numerator? The degree of this numerator is 3. So we're going to say n is 3. And what is the degree of the denominator? 5. Rule number 1 states that if the degree of the numerator is smaller than the degree of the denominator, in this case it is, right? Here, n is less than m, which becomes rule number 1, then automatically we get a horizontal asymptote of y equals 0. And that's done. Good night, go home. No other work to do. So this gets a horizontal asymptote of y equals 0. Sorry, hopefully I didn't say 1 earlier. Rule 1, horizontal asymptote, automatic y equals 0. That's it. That's what rule 1 states. Nothing more to it. Okay. Now let's go look at rule 2. Rule 2 says if the degree of the numerator is equal to the degree of the denominator, then the line given by the leading coefficient of the numerator over the leading coefficient of the denominator becomes the horizontal asymptote of the graph. So this happens if the degree of the numerator equals the degree of the denominator. So let's find a problem that looks exactly like rule number 2. So number 2, it's not going to work out. Here, n is 4, and here m is 3. So in this case, the numerator is bigger by 1. We have a case for that, but we'll get to that later. We want to find a problem where the degrees are equal. And that's going to be our number 3. Perfect. Here, the degree of the numerator is 2. The degree of the denominator is 2. So this means n equals m, which is rule 2. And if you have a rule number 2, this means that your horizontal asymptote is going to be the leading coefficients over one another. So 8 over 4 or just 2. That's it. You get a horizontal asymptote of y equals 2. That's how rule 2 works. So rule 1 and rule 2, really easy. Too easy, if you ask me, right? Okay. Also, make sure you are stating your vertical asymptotes. So here's a big mistake you can make. If you say, oh, my vertical asymptote is 1, this means nothing to me, and this may not mean anything to my math lab. Whenever you state vertical asymptotes, you have to state them as the equation of an actual line. So when you state a vertical asymptote, you must say x equals 1. That's how you properly state it. Do not make the mistake of just saying vertical asymptote is 1. It has to be x equals 1. Same goes for horizontal asymptotes. If you said my horizontal asymptote was 0, it's going to be incorrect. It needs to be an actual equation. 0 is a number, y equals 0 is a line. Just forewarning you, don't make that mistake. Unless my math lab wants you just to type the number in, then lucky you. Okay. Rule number 3, the hardest one of all the rules. If the degree of the numerator is bigger than the degree of the denominator, then we have no horizontal asymptotes. And the degree of the numerator must be bigger than the denominator by 1, only by 1. Then the graph of f has a slant or oblique asymptote. And the only way to find this asymptote is to use long division. I know. I'm sorry. There's no other way around it. And whatever we find as our quotient from long division will give us our oblique asymptote in the form of y equals mx plus b. We dread this. Rule 3, you're the worst. Why make us go back and do long division, right? Okay, so of course I have an example for rule 3. That was the second problem there, because look, the numerator is bigger than the denominator by 1. Here, n is greater than m by 1 value. So this is going to be rule 3, which means we use long division to find our oblique asymptote. I know, I'm sorry. But I'm doing it, you're not doing it, you're just watching. So you should be sorry for me. Okay, but why would you pick that problem for yourself? I know, right? Okay, so long division, I'll put the divisor first. X cubed minus x squared plus 1. Again, in my division symbol, I'll put the numerator, which is my dividend, and make sure you account for missing powers. 3x to the fourth plus 0x cubed plus minus x squared plus 0x plus 0. Okay. And now you can do your side work. I think we might be over that phase, but if not, do your side work. I'm not going to do it because I think I'm over that phase. So in order to get rid of 3x to the fourth, I'm going to multiply by 3x, which will give me 3x to the fourth minus 3x cubed. Don't get an x squared. I just get a 3x. All right. 3x to the fourth minus 3x cubed plus 3x. Cancel. Drop this down. That becomes positive 3x cubed minus x squared minus 3x plus 0. Okay. And then to get rid of 3x cubed, I'm just going to multiply by 3. And that'll give me 3x cubed minus 3x squared. Don't get an x, and you get a 3. And cancel. And I should get negative minus minus. So that should give me 2x squared minus 3x minus 3. And we can't go any further because x cubed can't go into x squared. And we have our answer. We don't care about the remainder. Our answer is the quotient. This is our oblique asymptote. So is y equals 3x plus 3. There you go. That's your oblique asymptote. Rule 3 is the worst, but it's a good thing we know long division. Hopefully. Okay. Last rule. I swear it's as easy as rule 1, 2, and 4. 1 and 2. Okay. Rule number 4. If the degree of the numerator is bigger by 2 units, there are no horizontal or oblique asymptotes. The asymptote will resemble a power function. So if you get the numerator bigger by 2, then all you're going to do is take the leading coefficients over each other and subtract the degree of the numerator minus the degree of the denominator. That's it. And do I have one for rule number 4? Of course I do. It's down here. So look at this. The degree of the numerator is 5. Degree of the denominator is 3. The numerator is definitely greater than the denominator by 2 units, right? By 2 units. Okay. Which means this is a rule 4, which means we'll have a power asymptote, is what we'll call it. And it's going to be y equals the leading coefficients over one another. And the leading coefficient of x cubed, if it's not shown, is going to be 1. So you're going to just get 2 times x. And now you're going to take the degree of the numerator, and subtract it from the degree of the denominator. And that should just give us 2x squared. Painless. Rules 1, 2, and 4, beautiful and easy. Rule 3, long division, hate it. But hey, we know how to do it, so the struggle. Okay, so those are your 4 rules for horizontal asymptotes. Ugh. More rules, right? So easy to remember, though. Okay. last one. Find the domain and range, intercepts, vertical asymptote, horizontal, oblique, or power asymptote of the given function. Okay, so first off, let's start with domain. It looks like we have a break in the graph at 3, because as we approach 3 from the left, this tail heads down towards negative infinity. As you approach 3 from the right, that tails head towards infinity. So this means that we'll never ever touch 3. Therefore, our domain is x cannot equal 3. And you know what that is in interval notation. Okay, then range. It looks like there's a break in the graph for your y values at 2. You have this horizontal asymptote. So this means as you come up to 2, there's a break, and then you continue on. So our range is going to be y cannot equal 2. Or negative infinity to 2, union 2 to infinity. Okay. Intercepts. Do you see any x and y intercepts from this graph? And I think we see that just right there. You cross the x-axis and the y-axis. So our intercepts are at 0, 0. And then next is, what is your vertical asymptote? Well, easy money. We don't even have to look at the graph. If your domain is x not equal to 3, your vertical asymptote is x equals 3. And then we have a horizontal asymptote, which is that horizontal line at y equals 2. There are no obliques. You don't see any slanted lines here. And there are no power asymptotes. When we say power, you don't see any parabolas or cube roots or anything like that. That's it. That's done. These were the properties of rational functions. The biggest takeaway is know your rules for horizontal asymptotes. Know how to find a vertical asymptote. And then know how to recognize by canceling out, by simplifying a rational function, whether or not your vertical asymptote becomes a hole in the graph. That's it. No more. Until the next time, y'all. See you there.